Hello and welcome to Chapter 1, Part 1 for Chemistry 100. This lecture will cover sections 1.1 to 1.5 in Chemistry in Context, 7th edition. This chapter, The Air We Breathe, focuses on relating the air we breathe to our health and how can we look at the chemistry involved? How can we learn a few things about chemistry while we learn about this important topic? So this first part will cover the composition of air, and we need to understand scientific notation. It's a way of writing very large or very small numbers, as concentrations of sometimes toxic substances can be very, very small and yet still be harmful. We need to be able to express that. Also, we're going to take a look at percent versus ppm. Parts per million is another way of, again, expressing those very small numbers easily and understandably. And then we have layers of the atmosphere, just a little discussion on the different parts of the atmosphere, because whether or not a molecule is in the lower part or the troposphere or the upper part in the stratosphere will make the difference on whether it's a pollutant or something beneficial that will help protect us from the sun's rays. So just to start with, our atmosphere is 78% nitrogen and 21% oxygen. And there's really not much else there, except we will get later on, we'll get into talking about carbon dioxide and the effect that's happening. But as far as the main components, we're really talking about nitrogen and oxygen. But again, as I just mentioned in the overview, sometimes it only takes very small amounts of certain molecules to have a large impact depending on what you're talking about, whether it's humans or our ecological system. So we have just a few ways to show that. There's a pie chart here on the left with the majority of the pie taken by nitrogen. Then the little bar graph also showing nitrogen versus oxygen and other gases, and of course the nitrogen is very large. People often make the mistake that, oh, I know I need oxygen to survive. Oxygen is the most important gas, and therefore it's the major or the majority of the gas in our atmosphere is oxygen. But that is not the case. And then this is just a little particle view on the right where we see out of, if we assume that we have 5 units of molecules, 4 of those molecules are taken up by nitrogen and only 1 is oxygen. And of course, I'm ignoring that 1% of the other gases for now, but we'll look at that in a moment. And notice that these molecules are composed of 2 little lobes. Those are really 2 spheres representing 2 atoms of nitrogen or oxygen coming together, and we'll see later that in nature those elements, they are paired up. So you always see O2, N2, the 2 representing the number of atoms in that molecule. So we call air a mixture. It's a combination of various substances, and we'll define how we talk about molecules versus elements later on. But what's important now is that you know it is a mixture. And some of the 1%, about 0.9% is argon, which is a noble gas. Carbon dioxide accounts for the rest. There is some water vapor and a few other trace elements that aren't quite as important. But notice that in this particular chart, it shows the percentages we talked about earlier, and then exhaled air, if I could say that correctly. Obviously, you could see now that the 21% that was in the inhaled air has dropped down to 16% because our body has utilized some of that oxygen. And lo and behold, we have exhaled some carbon dioxide. So the percent of carbon dioxide in air is 4% versus the original 0.04%. So here's our first Thinker Buddy question. You see the pause symbol in the upper right-hand corner. And I just want you to, I'll read the question, and then once I've read the question, go ahead and stop the video and think about it for a moment if you need to. So which of these gases is least abundant in an inhaled breath? Carbon dioxide, nitrogen, argon, or oxygen? So you may have paused it or felt confident that you could just wait a moment, but you should in general pause it. They may not be as straightforward, but actually carbon dioxide is the correct answer, A. It's the least abundant gas in an inhaled breath. There is actually a little more argon than carbon dioxide. So now let's go on to our discussion of very large and very small numbers. When we're talking about the number of atoms, we'll see that an atom is an incredibly tiny unit of matter. And so when we start talking about things in our day-to-day life, like a penny, the number of atoms in that penny is just astronomical. You can see here we have a number that has 3, 6, 9, 12, 15, 18, 19, 20 zeros. It has the digits 2, 9, 5, and then 20 zeros after it. I mean, we don't want to write a number that big every time we want to talk about this many copper atoms. And then, of course, the mass of a copper atom is very, very small. So you have, again, this time in a decimal form, 0 point, and then a huge number of zeros before we get to 104 gram. How do we talk about these? You should have been exposed to some of this and if you've had Math 20 recently, but just as a review, we use this tool to express these numbers, these large and small numbers, and it's called scientific notation. So here we have a lecture activity, which is a great YouTube video on scientific notation. You can take a look at that and then come on back and we'll continue the lecture. Okay, so now you've had a chance to get some information about scientific notation, and let's practice doing that. Take a moment and do some practice problems. Please write out the following numbers in scientific notation. A is 301, B is 40,000, C is 0.00005, and then after you write those out in scientific notation, I have two numbers here in scientific notation already, which I'd like you to write in standard notation, meaning put all the zeros in that we're trying to save time in not writing by using the scientific notation. So A in this problem is 6.52 times 10 to the 8th, and B is 7.745 times 10 to the minus 5th. Okay, so let's go through this at this point, now that you're back. So 301, the convention is to always put the decimal after the first digit. So you're never going to see 30.1, okay, times 10 to the first. While people would understand what number you're trying to represent, this is not the convention. So we don't write numbers like this. What we have down below here is correct, 3.01 times 10 to the second. Then part B, we have 4 zeros, okay, and there's only one digit of 4, so the way we express that is 4 times 10 to the 4th. And you may have seen in the video, one way to do this is start by putting a little decimal there and jump over 1, 2, 3, 4 times. That's where this 4 comes from. We have to jump 4 times to put, if you can imagine a decimal there. We don't actually put it there, okay, but if you can imagine it there, we had to jump 4 times to get to that point. And then over here in part C, we jump 1, 2, 3, 4, 5 times, but this time it's a decimal or fractional number. So we jumped over 5 times to the right, and that's why we have the negative, because that tells a person if they see this 5 here, they need to go 1, 2, 3, 4, okay, and 5, 1, 2, 3, wait, whoops, 1, 2, 3, 4, 5, okay, in order to get the original number. Now, in writing out the numbers in standard notation, you go about it the same way. Here, 6.52, you start here and you start hopping out. I'm going to do it in the answer. 1, 2, 3, 4, 5, 6, 7, 8. And that'll get you out here. Again, don't necessarily put in the marker at the end, especially if those zeros are not included here. You would never put a decimal out there. If you did put the decimal there, that would actually tell the person that every one of these zeros mattered in the measurement, which that is not shown here. You're only shown 3 digits. And in part B, again, the same thing, just start hopping out. Okay, but this time it's a negative, so you go to the left, not to the right. You don't make this a big number. The negative is telling you, hey, this is going to be a tiny number, so I'm going to hop to the right. 1, 2, 3, 4, 5. Okay, so now we are going to take a look at a little mini video on parts per million. I'll meet you back here. Okay, you're back. What we want to be able to do is convert between parts per million and percent. So let's just review or perhaps discuss percent. Okay, percent, if you have 1%, that means you have 1 part in 100, right? If you have ppm, say 1 ppm, you have 1 part in a million. And sometimes information's listed as percent, and sometimes it's listed as parts per million. So we want to be able to relate the two. And the way to do it, you can think of it 2 ways. Going from percent to parts per million. Okay, you could either think that, okay, I have to multiply by 10,000. Or you could think of it, I need to move the decimal places, the decimal place 4 to the right. Okay, either one. Okay, so an example of that, let's say we have 3%. Okay, 3% would be 3 times 10,000, which is 30,000. Or you could say, all right, I'm going to go to parts per million. I'm going to have the imaginary decimal here. I'm going to go 1, 2, 3, 4, put in zeros, and lo and behold, we have 30,000. So we have now converted percent to ppm. Now, what if we're given ppm and we want percent? Well, we've got to do it the other way. We have to divide. This time we divide, trying to do a division symbol here, by 10,000. Or we move 4 decimal places to the left. To the left. Okay. I hope that wasn't an inappropriate reference in that hip-hop song. Okay. So Now let's do an example of that. I've got a concentration of uh, 40 parts per million of lead in the eggs I get from my neighbor's urban chicken farm, because he lives in an old house and the house has a bunch of old lead paint chips in the dirt around his house, which his chickens peck at. And anyway, don't feed eggs. Well, don't feed eggs to your kids from urban farms. Um, so I want to know what percent that is. So I could either divide it by 10,000, or I can move it 4 decimal places to the left. So I'm going to start over here with the 40, my imaginary decimal place, and I'm going to go 1, 2, 3, 4. Fill in zeros there. And so this is where the decimal is. I like to put a 0 on the other side just so it's obvious that's the decimal. Decimal tends to feel naked without the 0 there. And then I put my percent symbol. So it's easy as that. Multiply by 10,000 when you're converting percent to ppm. And then if you have 10% of something and you want to express it in parts per million, you're going to have a lot of that thing in that system. But if you're going from ppm to percent, you only have a few ppm, say 5 ppm, 5 parts per million. Well, then it's going to be a very, very, very small, to get an equivalent percentage, it's got to be very small fraction of that. You can think of percent as parts per 100. Okay. Let's go on here. Let's do a little thinker buddy, which lists the amounts of lead in order of increasing concentration. A, we have 1% is less than 1 ppm is less than 1 parts per billion. B is 1 ppm is less than 1 parts per billion is less than 1%. C is 1 parts per billion is less than 1 parts per million is less than 1%. And D is 1 parts per million is less than 1% is less than 1 part per billion. Okay, hopefully you paused the video, had time to think about that. Don't be afraid of hitting that pause button. And let's look at the answer. Well, the answer is C. We didn't specifically talk about parts per billion, but you can think parts per billion. If I have 1 part in a billion parts, that's going to be smaller still than 1 part in a million parts. And that's 1 part in a million parts is going to be even less than 1 part in 100. So let's now apply this. We had to give you a little of the math background to talk about air pollutants, concentrations, and risk assessment. Risk assessment is the method in which governmental organizations and other companies, companies you may have heard, about, large corporations making a risk assessment as far as how many people will get sick from their product, how much money they'll lose from those lawsuits, versus how much money would it actually cost to just remove that product from the market. That, unfortunately, is a very negative way of looking at risk assessment. But we're going to look at pollution, hopefully the risk assessment for pollution, as a way to look at risk assessment in a positive fashion. We want to minimize exposure to pollutants in a sustainable way as possible that puts people at the least amount of risk without having too much of any other impacts on the environment or on the economy. So in terms of air, we set our air quality standards in 1970 with the Clean Air Act. Okay, air quality standards. Now, what are these standards? I want you to, even if you don't know, maybe just think about for a moment what these standards were and how they decided what pollutants to monitor, and what concentration was appropriate. No idea? Okay, come on. Just work with me a little. Yeah, they probably got scientists involved, right? They probably didn't have, the congressman who came up through, you know, uh, his ownership of a pizza business try to decide which pollutants were harmful. They probably brought in scientists, right? And what they did was they looked at, okay, well, what do these scientists know about toxicity? What do they know about the health hazards? Um, if Billy has, exposure to 5 parts per million lead every day, is that actually going to have a biological impact? How toxic is lead to children? And we know it's fairly toxic. And of course, I'm talking about lead. I should actually be talking about what's in the air, such as exposure. So, what degree is this substance present in the atmosphere? You could, of course, talk about risk assessment in, the land and in water, but we happen to be talking about the atmosphere. So, what concentrations are there when you're standing by the side of the road? How much of these fumes from car exhaust are you taking in, and how toxic are they? And then we do the kind of what seems to be a little cold calculation in terms of if you work alongside the road every day, inhaling the fumes of cars, uh, what are the chances that you'll actually have some kind of health uh, problem down the road? So we need to look at what kind of exposure you've got, and we've got to see, based on that exposure, will anything really happen? We don't want to go overboard in saying, okay, we need to eliminate all of traces of this particular molecule, when in reality, the oldest man in the world happened to have a fairly, high concentration. It's only certain people who work, in auto body shops or something of that nature who get exposed to a particular chemical excessively that we see the health impact. So we have to somehow evaluate a point when a molecule concentration is going to be a problem. So that's our risk assessment. And here we have a table, the headings of air pollutant, the permissible limit, and the effect of the pollutant. And we're looking at carbon monoxide, ozone, sulfur dioxide, and nitrogen dioxide. The reason being is these are common air pollutants, most of which are caused by the transportation industry, by vehicles, commercial and industrial and personal. And we have limits. So these limits were set looking at the toxicity and getting a sense through past evidence, really. What evidence do we have that people exposed to something higher could have a health risk, could have health consequences? So for carbon monoxide, over 8 hours, that person cannot be exposed to more than 9 ppm over an 8-hour period. But yet it says for 1 hour, a person could be exposed to as much as 35 ppm. What is that difference in the values? Well, scientists have seen that your biological system, a human, can bounce back being exposed to 35 ppm of carbon monoxide in an hour. But if you're exposed to 35 ppm through the entire working day, you could have some serious health consequences. So they have to lower that number down, because no longer is the body getting a break after an hour and able to replenish any disruption of oxygen. Okay, it's for 8 hours straight, it is getting this poison, carbon monoxide, which disrupts delivery of oxygen through the body. That's what kills individuals who turn on their car, don't open their garage door, and their car is running while they're in the garage. And unfortunately, what happens first is you pass out, and then, of course, if you pass out, you obviously can't escape the situation. The concentration of carbon monoxide goes much higher than 35 ppm, and you basically suffocate through lack of oxygen. The carbon monoxide kills you. And we have other concentrations for the ozone, sulfur dioxide, and nitrogen dioxide. You can see these are more toxic yet than the carbon monoxide. And again, it's just the evidence we have. The average individual for ozone, okay, it has to be 0.12 ppm in an hour. It can't be more than that, because that could cause respiratory irritation. It can cause serious consequences. And again, if they're exposed to ozone straight for 8 hours, that value has to be less. It's 0.08 ppm because the body didn't get a break. It didn't have a chance to recover and do any momentary healing that could occur. And you see that these values are similar, not the actual magnitude, but you see that pattern in hour versus 24 hours, etc. So now, please take a look at the video 3 in part 1 of chapter 1 on particulate matter. What you're going to see is it's going to show nice representations, and particulate matter is abbreviated PM, and the little number 2.5 after the M is referring to the diameter of that particulate. And then PM10 is talking about a diameter of 10, and it happens to be micrometers, which is a very small unit, but you'll see that in the video. Okay, now you're back. Got a little bit of information about the size of particulate matter. And when we talk about particulate matter, we're talking about dispersed matter. So not just molecules, it's more like clumps of molecules, and that can happen in dust, mists, fog, smoke, soot, smog, pollen. So this is what makes up particulate matter, and the size makes a difference because how it interacts and how it gets into your lungs. And if it's a particular size, like the 2.5 micrometer, it can impair your breathing. Both sizes can reduce visibility because they scatter light. You can also get, wonderfully enough, you get toxic chemicals, heavy metals like cadmium and nickel, or even organic molecules like pesticides from the ground, the side of the road, absorbed or stuck to these kind of super molecules, this particulate matter, and then kicked up into the atmosphere and inhaled by all of us. This graph here on the next slide shows percent on the y-axis and years on the x-axis. We have near the top 0%, and it goes up to 40. And it's showing the deviation off of 0%, which is our national standard. So it's saying how much is it deviating from what we've set as the standard for how much of this pollution can exist. And you'll see the averages. It's taking averages in various cities. And the averages look very good. Carbon monoxide in 1980 was basically where we set, very close to the standard limit we set. And it has decreased more than 60%, 80%. The levels in 2006 were much lower. Sulfur dioxide has gone from being much lower than the national standard to begin with to from 60% to 80%. So we're doing pretty good. Particulate matter has decreased a little bit from close to -10% down to -20% below the standard. Ozone started above the national standard and is now below, about 5% below. So, looks like we're doing okay. The problem is these are averages. You have to remember what an average is. And the period of time that it's taking, is it doing it over a year? Is it saying during all of 1980, this was the concentration and it was 20% above the average? But that's a problem, right? Because what if you have very little ozone or very little carbon monoxide most of the year? Fine. But if you have a couple days where that concentration is so high that it can affect human health, you have a problem. Okay, so here we have some days. We're looking at days of the year in different metropolitan areas where that concentration went above what we consider a safe exposure. And so we've got Los Angeles. We all know Los Angeles is infamous for its smog. 62 days out of the year, and I believe this was done in 2000. 62 out of 365 days had an unhealthy level of ozone. 38 out of 365 days had particulate matter 2.5 greater than our safely allowed value. We're here and filming this from the Pacific Northwest in Portland, Oregon, and we like to see that Seattle had only one unhealthy day of ozone and 4 unhealthy days of particulate matter. We get a fair amount of air moving through, rain, wind that pulls out the pollution. And we'll talk a little bit more about the air in Los Angeles is a little bit trapped in those valleys. And that causes a problem. They really need to be more careful of the pollution than we do in the Pacific Northwest. But everyone actually needs to take into account the pollution they're generating. Even if it doesn't impact them directly, it might impact a neighbor. And we'll talk about that later with acid rain. So let's go ahead and introduce a few important details about our atmosphere as far as how we talk about it as scientists. And what we have here is a picture with a tall mountain and next to the ocean to give an idea of the height used to define the different parts of the atmosphere. So here we have labeled the troposphere, which is from sea level to about 10 kilometers above the surface of the Earth. So you can see it's a little higher than the mountain tip, and that's known as the troposphere. Then from that 10 kilometers to the 20 kilometer point and beyond is what we call our stratosphere. And in the stratosphere, part of the stratosphere, around 20 kilometers or so, a bit above that marker, and a bit below that marker is the ozone layer. Now, we talked earlier about smog and pollution being trapped in the Los Angeles area, or in any area. Most highly populated areas have smoggy days. And what happens is what we call a thermal inversion or a temperature inversion. Normally, you can see on this upper slide here, normally you've got warm air near the Earth. The sun hits the Earth Earth absorbs that heat energy, and then it's re-radiated out. So we're nice and warm near the surface of the Earth, but as you get further away from the Earth, the air gets cooler and cooler. That's why there's always snow on the tops of mountains, right? It's much colder the higher up you go. And we also know that warm air rises. So when we have this normal system where with the warm air starts floating up, mixes with the cool air, gets out of the area, away from the city. We don't have any pollution problems to a large degree that day. But what happens, and particularly when you're surrounded by valleys and landlocked areas, you can get this warm layer forming over the city called the warm inversion layer. And when that happens, you now have cooler air near the surface of the Earth than a warmer layer. Well, cool air doesn't really rise through warm air. It's the other way around. Warm air rises, like when it's a very hot day in the summer in your house, upstairs is quite warm because that warm air rises. But when you have very cool air with warmer air above it, it doesn't rise, it doesn't mix. It's like your basement if you have one. The basement stays very cool because it has that warmer layer of where people live above it. There's also other things going on. It's underground, and the Earth is a reservoir for heat and maintains a very constant temperature. That also is taken into account. So here we have an image of some smog, a situation, and you already saw a little bit about China's pollution problem. So often over Beijing, you have this problem of this temperature inversion and just mass amounts of pollution in general, and so you get the formation of ozone and smog and other things. And then here we have Paris, and just looking down one of the main arteries or historical streets, at least the Champs-Élysées, and you can see it's very, very polluted, very smoggy looking. In winter haze, there's been a temperature inversion. Oh, so you're going to take a look at China's current pollution problem now. You haven't seen it yet. Ignore what I said earlier, but this is you'll see that it's quite an amazing thing in terms of pollution problems going on in China right now. It harkens back to the Industrial Revolution at the turn of the 20th century in the United Kingdom, where pollution was rampant and caused deaths even in certain urban areas. Now you're back, and this slide here just shows the ratings of the air quality that governmental organizations use to communicate in a very straightforward fashion to the population, right? We love to do the color scales. The green is good, the red and super dark red is bad. And so you don't need to know much science. You just know if you've got this arbitrary scale. They take the scientific data, the numbers, the ppm of the particulate matter and the ozone, and they say, okay, we'll look at them all, and they're all looking pretty good, so it's green. Or we're looking at them all, and don't go outside. It's the air is like eating soup, and you're probably going to have an asthma attack. Okay, so you can check wherever you live. You can check if you're going to spend a day outside and you live in an urban area downtown and you're going to be working on like a balcony garden. You definitely should be checking the air quality index. Maybe it's not a good day for you to do that if you're breathing a lot of air, if you're outside quite a bit. So here we have a Thinker Buddy question. This graph shows the source of the pollutant carbon monoxide in the atmosphere. And it's a pie chart, and the majority of the pie chart, 76% is taken up by one type of either industry, part A, or A, option A, transportation, B, power plants, C, or natural sources, D. So which do you think produces the majority of carbon monoxide? Well, as we mentioned earlier, carbon monoxide is one of the pollutants that comes from car exhaust. That's what would potentially cause accidental death in a closed garage. And it's also what is spewed out of all our tailpipes. And there are so many cars generating so much carbon monoxide that it's actually the transportation industry and commercial and public that causes the majority of carbon monoxide pollution. So that ends Chapter 1, Part 1, covering sections of the text 1.1 to 1.5. Is it time to take a break? You may want to read through the corresponding sections of the text if you've not done so already. Some people actually find it easier to review the text and then watch the lectures. Whatever works for you. You could read the text afterwards. And yeah, I'll leave it there.